Hello everyone again. Let's keep talking about the Halliday and Resnick book, 10th edition. And about, in this case, in this part of the discussion, chapter 26, current and resistance. So there we go. Chapter 26, current and resistance, from the Halliday and Resnick book, formerly known as the 10th edition of the Halliday and Resnick book. And let's see what we can say. Problem number 35 from chapter 26 is what I'd like to talk about. What we can say here, let's read it out. Those of you who have had me before as a teacher and have maybe looked at some of the content that I've provided, either through a live presentation or on film in some other context. We did something on film similar to this elsewhere, and so you can. I think many people will be able to access this this similar type of problem that was done in another place. You should be able to find this in some of the work that's been provided to students when I've done some of the work in the past. So let's kind of look at the same thing again. Here's this sort of cone-shaped figure, like truncated cone. If this thing went all the way across, if this went all the way to the limit, it would be a cone, but it's a cone that's been cut right here and a cone that's been cut right here. This line has no significance, just telling you that the small cross-sectional circle, the smallest cross-sectional circle, has radius A, and the biggest cross-sectional circle has radius B. So smallest cross-sectional radius, for the smallest circle present, that smallest radius associated with the smallest cross-sectional circle is A, smallest radius, and the biggest radius present in all the cross-sectional circles is associated with the biggest cross-sectional circle, and its radius is B. What they tell us is, for problem number 35, current is set up through a truncated right circular cone of resistivity 731 ohms times meters. The left radius, the small radius, A equals 2 millimeters, right radius, B equals 2.3 millimeters, and the length is 1.74 centimeters. The length, capital L, is 1.74 centimeters. This isn't really drawn to scale if that's the case, guys, but again, it's just a rough guide. So A is 2 millimeters, the small radius A is 2 millimeters, the big radius B is 2.3 millimeters, and the length, capital L, is 1.94 centimeters. Assume that the current density is uniform across any cross-section taken perpendicular to the length. What is the resistance of the cone? Okay, some of the wording even can get a little confusing, but we're going to do things similar to what I've done in the past. Those of you who have had access to some of my earlier work will basically see what the argument is pretty well here. See what they're trying to say here, guys. And once again, everything from chapter 26 that I had happened to do, and that's certainly not everything that's there to be done, but it's some good problems that I thought give us a decent feel for much of what's going on in each of the chapters, chapter 26 in this case, but in other chapters too. Everything that I thought was relevant in a somewhat very abbreviated format, and abbreviated, given that our time is very much abbreviated, cut short a little bit, all those answers will scroll at the end of every chapter, of every video, of every film pertaining to a chapter. All those videos will scroll at the end of every chapter. So put another way, as I've already kind of said, for chapter 25, all of the solutions of the chapter 25 problems that I deemed appropriate, albeit in a little bit kind of an abbreviated manner, all those problems that I had worked out, they're all going to scroll for you for chapter 25 in the film for chapter 25. for chapter 26, everything in chapter 26 will scroll as well. So you have to look at all of the videos, I guess, to get all of the scrollings, but they're there when you do this. All right, well, there's a lot that can be said here, guys, to make sense out of this thing. We are told that there's a few, I mean, it's based on earlier conclusions that have been drawn, I guess you could say. I don't know how far back I want to go. So, I mean, it's proved in the book. We know that we can find, if we stick around and actually do it like a derivation of what's going on, you guys, there is a number of things that are pretty interesting that we need to kind of just keep in mind, at least in the back of our mind, when we're doing some of this, or actually I should say that better, maybe keep it first and foremost when we're doing this stuff. The resistance is directly proportional to the resistivity times, now we got to be careful here, guys. This row right here can, like I said, some of there's repetition of some of the symbolism, guys. The resistance is directly proportional to the amount of resistivity associated with the material and directly proportional to the length. The longer the wire, the harder it is for you to get electricity to go through it, so there's going to be more resistance. And it's inversely proportional to the cross-sectional area of the wire. In other words, the thinner the wire, the harder it is for you to get electricity through it. What's the ideal situation? Well, if L is small and A is big, this is a small answer, and a small answer times this is going to give you an optimal situation for low resistance. But if something's really long, if the wire is really long, it's hard to get from one place to the other. That makes sense. So there's going to be more resistance. It's directly proportional to resistance. Resistance is directly proportional to the length of the wire, and it's inversely proportional to the area, cross-sectional area of the wire. If there's a real small cross-sectional area, that's a small number. Well, a small number divided into something is going to give a big answer. There's a lot of resistance. If there's a real small cross-sectional area, you're going to have a hard time conducting electricity. And if it's very long on top of it, that's going to be hard to conduct electricity as well. A lot of resistance if L is big, and a lot of resistance if A is small. Big divided by small is huge. There's going to be a lot of resistance. So that's one thing to keep in mind when they talk about resistance and how it relates to resistivity and the like. So, true. They say another thing. Sort of be careful here, guys. So they say a bunch of things, guys, in the book here. I guess they say, Halliday and Resnick's book, as we have done several times in other connections, we often wish, to take a general view and not, as we have done several times in other connections, we often wish to take a general view and deal not with particular objects, but with materials. Here we do so by focusing not on the potential difference V across a particular resistor, but on the electric field E vector at a point in a resistive material. Instead of dealing with the current I through the resistor, we deal with the current J at the point in question. Instead of resistance R of an object, we deal with the resistivity rho of the material. The resistivity rho, and this is, we're not going to, and this rho is a little different from It's not charge density, guys. So you got to. That's why I was a little concerned the language that gets used on this. But you got to. I mean, there's going to be repetition in the language sometimes. Rho is the resistivity. Rho is the resistivity. It is the E field being applied divided by J. And J is basically the current density, they call it. And that's basically I over A. So what you have here on the look here, let's see. There's a lot of ways to define J, guys, and it's how we do it, but it's going to be basically I over A. And for the resistivity, so we can kind of get an idea of some of the stuff that's going on here. But J is associated with current divided by A as the current's passing through. There's a lot of flexibility how some of this gets said and how it's applied. I don't want to get into that too much. I want to just say it as this. There is a cross-sectional area A for our purposes, and there's a current I, and I divided by A would be the J. Okay. Some of that's useful. Exactly how much we're really going to look at it, we'll have to see about it. But we could say some things to maybe give us some idea of what we're going to do here. There is a lot of linearity in this whole process. There's a lot of linearity in this process, guys. In other words, this thing, if you just take the outskirts of it, this thing looks like what you think it looks like, a line segment. This also looks like a line segment. Well, I'll tell you what, if on the upper end of this right here, that's a height of A, and on the upper end of this is also a height of B. Well, there's symmetry here. We're going right down the middle. This is a height of B. And this length is L. I guess, you know, there's a number of ways you could actually look at it to get there. Let's say a few things. Let me erase a few things, and we'll see what we can say. J, as we said, was I divided by A. R squared varies. Has a maximum value. R is equal to B is the maximum value. R equals A is the minimum value, and it just goes like this. Well, wait a minute. How does this stuff climb? I mean, you can start it at A. I guess there's a slope here, guys. If you allow me to tinker with this, I almost don't want to, but here we go. Let me do it. Let me draw a right triangle, and actually this is by far not a great drawing, but that's something like a right triangle. What's the slope of this line? Well, it's at a height of A, but ends up at a height of B. It rises B minus A. It's the rise. This distance right here is B, right? And this height right here is A. If you take the A straight across, this is A right here. This is A, this is A, and this is B. B minus A is this right here. B minus A is this, and it runs this whole distance, which is a distance L. That's the slope. We'll start here at x equals 0, and it goes here all the way across to x equals capital L. So if you multiply it by x, you'll get the x is starting at 0. As you traverse all the way to L, you go like this. And yeah, I know, but you started at A. And that's your R. So let me write that a little bit better in a second, guys. They have told us a lot. Let me come right back to this. But let's see what we can say here a little bit. Got to replace the erasers pretty soon, guys. It's not the greatest circumstance right now, but let's see what we can do about it. Let me throw that out of there for a second, guys. Just write it down again. This is kind of an awkward location for the whole process to be written here. Basically, we're talking about the slope was B over A. The slope was the quantity B minus A, rather, over L. If you multiply it by X, that's the change from the original. The original height was A, and that's going to give you R. So to put it more like y equals mx plus b, you just put the R out in front, guys, is what you're doing. So basically what you got is, and that's what I was kind of writing here. Let me just write it in a little bit different order. Yeah. Mx plus b, well, it's really not b, but it kind of behaves like the y-intercept. It is the y-intercept. If you're drawing it here, straight up, bam, here's where it intercepts. It intercepts at 0, comma a. So that is your y-intercept, right at that point. Okay, so you've got this to give you a formula for R as you proceed to walk from x equals 0 to x equals L. As you proceed to walk from x equals 0 to x equals L, bam, R is changing. How's it changing? Well, it starts at A, and it goes all the way up to B. I mean, here's B, and it started down here. A, it's the same A that's over here. So it's looking pretty good that way, guys. Some other stuff on the side here. I just about started it over here, guys. We've got some of this stuff. We can come back to it and use it. J equals, well, there's a lot to say here, I guess. J equals I over A. So I'll just put this kind of over to the side here. J equals I over A. And let's talk a little bit. Yeah, if the resistivity is equal to, resistivity is directly proportional to the E field divided by the current charge, the current density. What does that mean? Well, there's not a lot of resistivity, guys, if there's a lot of current going through. If J is a if J's, for any given E, if J is a very, very big number, for a given E now, E, let's just hold it steady. For a given E, if you were to change J and make J into a very big number, E divided by something huge is small. Yeah, there can't be a lot of resistivity. If for a given E field, you got a lot of J going through there, a lot of current per unit area going through there, yeah, there's not much you can say. There's not much there that's causing a lot of resistance, and resistivity is a measure of the tendency to resist current from flowing. Well, if there's a big J down here, guys, that's a small answer, not a lot of resistivity. If there's a small amount of J, there's a lot of resistivity. Okay, that makes sense. And that's the way they define it. So let's multiply by J on each side and divide by rho. And that's not charge density or volume charge density as it's been in the past. J is, rho is different. It's resistivity. Multiply by J on each side and divide by rho, and you got this. Well, wait a minute. J is equal to I over A, and J is equal to this. So J equals J. I over A yeah. Well, what do you want to solve for? Depends what they're asking, I guess you could say. I tell you what, I mean, let's take a look at the, this is true, and there's a lot of games you can play with it, I guess. At the end of all this, you could say, let me solve for E, magnitude of the E field. Go rho I over A. Rho I over A, or I rho over A. A is pi r squared. A is pi r squared. So that's kind of where they're going there. Yeah, be about right, you guys. So, I mean, what we're saying here, I guess at the end of the day, we're trying to find the resistance. Well, I guess there's a number of ways to find the resistance. One way to do it is, establish relationships, find, we know that I, V, and R are very closely related. So if I know what I is, or if I know, if I know I and V, I can find R. If I know V and R, I can find I. Et cetera, et cetera. So maybe that's the way you want to look at the argument, how we're going here. So let me just walk you through some of this. Okay, we made that statement. So where are we trying to go here? Well, let's try to get a good look at this. All right, we got this. So let's see what we can say, guys. The way I kind of did the argument, the things about which we have spoken imply a lot here. Well, let's look at E. E equals I rho over the product pi r squared. What does that mean? Well, E equals I rho over pi r squared. Here's pi, and the way I wrote it, I think the way they would write it in other places as well, guys, just to kind of play it safe. Maybe it's maybe a little easier to look at. Pi is this. R is A plus B minus A times X to the negative 2. Why is that? Well, this is R, but I want, this is R, and then this thing is R, and if you square it, you got R squared. Yeah, but I want it on the bottom here. But I don't have room, so I wrote it like this. So I wrote to the negative 2. Okay, great. Maybe this will walk us through what we need. I mean, it is believable that if there's a lot of resistivity, but there's still a lot of current, and it's happening over going across cross-sectional areas that aren't that big. See, this is kind of interesting. Let's come back here. Why do I know? How do you know you got a huge E field in play? You've got a very large E field in play if there's very much current flowing, and there's a great amount of resistivity. But despite the fact that rho is a very big number, there's a lot of resistivity, there's still a lot of current. A lot of current despite a lot of resistivity divided by, you're crossing cross-sectional areas that are very small. If this is very small, something very small divided into something huge is mammoth. Big times, if this is big and this is big times big is huge. Huge divided by tiny is even more huge. It's got to be a big E field that's doing the whole thing. Maybe that's a little bit of a kind of a gut feeling as to what's going on with that. So look, the bottom line is this R squared you know, you want to put all of this underneath here and then put a regular square on there, not have it be the negative thing here. But I, for our purpose, say, hey, we don't have room, I'm going to go to the negative power, and there it is. Okay? So that's E. Well, that's important. It's important, so how are you going to do it? I mean, since you know it is important, I agree. How do we get the job done then? Well, we know that the potential difference is always, you know, the magnitude of it is non-negative, but for our purposes, we're going to go from 0 to L of E dx. E vector dot dl vector will give you the magnitude of the potential difference. The negative sign is put in there for a reason, for bookkeeping. Doesn't affect the magnitude though, that's an important thing. So what do we have here, guys? I mean, we're saying, you know, what's the potential difference that has to be in play for that to take place? Well, if we're looking at it like this, when you actually do it, the potential, you know, and things go from low potential to high potential. I'm sorry, from high potential to low potential is what the flow is going to be. Again, the way the bookkeeping's done, guys, you're talking about positive charge carriers being responsible for the current. So let's write it like this. In terms of magnitude, the negative wouldn't really be there, or at least you take the absolute value of this and you'd find the magnitude of the potential difference and find out what's going on. But it's E vector dot dl vector. E vector dot dl vector, the integral of E vector dot dl vector will give you the magnitude, or at least the potential difference within a sign. If you get the absolute value of both sides here, guys, the magnitude of the potential difference will be the absolute value of the integral of E vector dot dl vector. Okay, well the dot dl vector is dx. They go in the same direction, so the dot product is E dx times the cosine of 0. They're right in line with each other. The cosine of 0 is 1, so you can leave it like that. So there you go. You're looking at all the situation looking essentially like this. If this is the case, let's play the game that we have basically set forth here, guys. Well, everything we wrote we're going to use, so we just don't have room to have it on there continually, but everything that we've brought forward we're going to use in one degree or another. Well, here goes. Using what we've said, let's get some answers here. We've got and what do we say? Well, we already said what was what, right? We said I rho over P r squared is the E vector, or the magnitude of the E vector. I rho over pi pi r squared on the bottom, these are constants, so I could take them out of there. And you've got a plus b minus a over L x. Okay, I wrote that slightly differently, but that's not a big deal. We know what I'm talking about. Okay, I didn't need probably to write, probably wrote more parentheses than necessary, guys, but I think you can kind of see where I'm at. And now it looks worse than it did. Let me just write it anyway. B minus A, I feel like writing it like that, even though I didn't write it like that in the notes, and I had it here. And then I got this. And that's going to be the negative 2. All this is underneath right here. But I had to take him out of here. I had to take that out of here and leave it, or put it underneath an integral because it's constantly varying. Whereas the pi, the I, and the rho are not constantly varying. There's one I. There's one current for that whole thing. Despite how difficult it looks, there's one current I racing through here. Okay? So we're looking at it like this. So because there's one current I racing through here, you leave it as one current I. There's one rho. It's the same material. Material is not changing. The composition of it is the same throughout, just different shape. There's the same rho, the same I, the same pi. Underneath is r squared. Yeah, the r squared varies. So you got to put 1 over r squared, which is the same as all this, which is r to the negative 2. It's all of this underneath 1. 1 over all of this squared. Well, that's the same as all this to the negative 2. And then you put the dx right there. That's essentially the argument, guys. It's as this approaches, as we do this. There's a lot to be said. I mean, it's, you know, the way I showed it in the notes, you can sure argue a whole bunch of ways of how to say something like this, you know, that's for sure. I'll tell you what I'm going to do. This thing right here, you guys, let's take a snapshot right here. We can use the power rule right here and then take consideration of the chain rule in a sense. This is a constant. Don't let it scare you. Plus, this is a constant times a variable, plus a constant times a variable, done, plus a constant, the whole thing taken to the negative 2. Is there an integral there, and is there a pretty easy integral there? Yeah, by the power rule, you can add 1 right here and go, add 1 right here and then go, so it becomes, if you were integrating this, let's kind of say it like this. If we were getting r to the negative 2, dr, let's say, what would be going on here? It would be add 1 to that, and then go 1 over negative 2 plus 1. And you end up getting 1 over, that's negative 1. 1 over negative 1 is negative 1. Negative 1 r to the negative 1. Negative 1 equals, so you'd be getting this. Yeah, it gets a little messier when there's all this business going on in there. It's like I said, it's easier done than actually said. This is kind of the argument that's taking place. This is the R. Yeah, there's a difference though. There's a U right here. In other words, if I was just trying to figure out a good way to say this, short of actually doing it. You're using the chain rule in the integration, believe it or not. You're basically going to say, wait a minute, there's got to be a way to get this, and here's the way to get it. Let's take I rho over pi, leave it alone. This right here. This is u. This whole thing right here is u to the negative 2 dx. So integral of u to the negative 2 dx, where u is equal to a plus b minus a over capital L times x. That's u, sure is. Du dx is just this. It's the slope. Makes sense to me that it would be the slope. It's the slope. So, there's a lot of ways you could go here. I don't want to get, I've been saying I don't want to get too adventurous with this thing, and I'm about to go just exactly in that direction. So that's du dx as is. How would you solve that for x? How would you solve that for dx? What do you say you multiply by dx on each side? Multiply by dx on each side, then multiply by the reciprocal of this on each side, which is L over b minus a, and the du was there. There's your dx. That's what dx is. Well, what is that? That's basically, there's other ways to do this. They tend to be simpler. I'm trying to be a little more rigorous about it. I mean, you can argue how justified that is and how much that makes some sense, and I'll just give you another look at it as well. But, I mean, dx equals L over the quantity b minus a du. L over b minus a. What's this? What happens here is that's L over b minus a. This right here is going to be negative 1 u to the negative 1. We already kind of did that argument. With x equals, with u equals this for a given value of x, it doesn't matter. I know the u's are going to be different. The limits of integration vis-a-vis what the u's are going to be are going to be different. How different are they going to be? You're going to plug in x equals 0 in here, for this particular value for the u's. You're basically going to plug in x equals 0, and you get the u is going to be a. You're going to plug in x equals L, and the u is going to be b. It's going to go from a to b rather than from 0 to L. So these integrals are going from a to b, as opposed to earlier. Forgive me, with the dx. With the dx, it was going from 0 to L. Here it's going from A to B. That's only because you're plugging into here, guys, to actually get the answers here. If you just leave it as, the whole entity as something going at something going at its own speed, going at a speed associated with this. There's a lot more to say on this, guys, but these limits of integration aren't a big deal. You can go from 0 to L, and that's 0 to L here. That the A to B is the same as 0 to L. You're just plugging in. You're plugging in 0 right here to get the A. You're plugging in capital L right here to get the B. You're still dealing with x equals 0 and x equals capital L. Not a big deal. Let me not say much more on that. But that's a big answer. Well, how big an answer is that? Well, it's big in the sense that that's the same as -1 L over B minus A U to the -1. Well, wait a minute. I erased it, but you guys saw the speech. Nevertheless, that's A plus B minus A over L absolutely true. Yeah, we forget. We had this in front as well. I solved it here, not counting this. Not counting this, I solved this. And I got that. That right there is this right here. So from here, all of this, yeah, this part of it I just did, and it's the same as this. So what's going on? Well, what's going on is you simply just put the other stuff right there, and let's just see how the whole thing plays out, guys. And I'll show you another way. Like I said, this stuff is, forgive the speeches I'm delivering here. Give the erasers as well, guys. They're not the greatest right now because, understandably, at the time at which I'm doing this, there aren't people around to be looking at this. So that's certainly no one's fault on that. Okay, so what does that mean? That means to the -1. I wrote it a little differently in my notes, but it's the exact same thing, you guys. Let me make sure for some reason, I might be off by a sign here, guys. For some reason, I'm having a hard time believing this. Oh, yes, correct. There should have been a negative sign here corresponding to the language they're using of a negative sign there. So there's a negative sign there. That should be fine. All right, let's throw all the mumbo jumbo out of there, guys. Let's not worry about this. Let's not worry about this negative sign. So let's not worry about that negative sign, nor that negative sign for now. Let's just, it's there. We will worry about it at the end, but we got negative signs all over the place. I tell you what, the negative I rho over pi, put it over there and have it out of your mind. How does this work out, and how am I getting this for an answer? And when I am done getting this for an answer, I do have to evaluate this with the x's under consideration, and that is from x equals 0 to x equals capital L. Okay, what's going on? How did I get that answer? You're basically finding the integral by using the product rule, but there is a subtlety. There's a real subtlety to all that's going on here, you guys. As we have here, the real subtlety is there's something going on here that complicates matters a little bit. Well, okay, so what? Is it going to be a real big problem? Not really. It looks much more complicated than it actually is. That's a constant. That's a constant, not going to change, and it's being added onto this constant, though somewhat potentially at first glance confusing. It's simply a constant. Don't let it be confusing. It's b minus a constant minus another constant. It's big number minus small number, positive answer, divided by a positive number, positive answer. It is the quantity b minus a, divided by L times x is the slope of that line, of that outline we saw. The quantity b minus a over capital L is the slope of that line or outline. So this slope, the quantity b minus a over capital L times x plus a will give you the radius as we proceed moving with x. Pretend this whole thing's just an r to the negative 2. If you integrate r to the negative 2, you got negative 1 r to the negative 1. Great. There's a problem here. I got to somehow figure out the integral such that if I were to take the derivative, I get back to where I started. Can I do it? Yeah, I just need to get back to here. Well, I'll tell you what, I got this whole thing right here. I want you not to worry just yet, and I'm just going to say this. What's the reciprocal of the slope? The slope, the quantity b minus a over capital L. The reciprocal of it is L over the quantity. It's L over the quantity b minus a. Maybe I got something here. Tell you what. Look at all this. That's just a constant. Don't worry about it. Take the derivative of all this with respect to x. The negative 1 comes out in front. The negative 1, we take the derivative, the power rule, the negative 1 comes out in front, and it's negative 1 times negative 1, that's positive 1. Negative 1 minus 1 is negative 2. We got all of this to the negative 2. Then, by the chain rule, the derivative of this inside is the quantity b minus a over capital L. Bring it out in front. The quantity b minus a over capital L, the quantity b minus a and the quantity b minus a down here cancel. L down here and L up here cancel. You already got the negative 1 and negative 1 when multiplied together to give you 1. They're out of there. You get the quantity a plus the quantity b minus a over capital L times x, the whole thing taken to the negative 2. You get that when you do the derivative of this. It worked out just fine. This guy was on the outskirts, and so was that. Well, here it is. We're consistent. Here he is, and here it was. We left it there and put it here, and then we just said, okay, I'll tell you what. Take the derivative of this thing. Do you actually get, forgive me, the integral of this thing will give you all this. Really? Sure. The integral of this thing right here, ignore this, and just put it right here. So they're ignored right now. The integral of this will just give you this. You think so? Yeah, I think so, because if I take the derivative of this and apply the product rule and then the chain rule, exactly that is what I get. The item that was being integrated is what I get. I don't get the integral, I get the item that was being integrated. Okay. Simple as that. Well, whatever data they give you, plug in there and then get the answers. I mean, they're giving us, that is it. I mean, that's the hardest part of the whole problem, you guys. If you go, certainly a whole bunch of things that can be said here, guys. I'm just debating what I'm going to subtract here. All right, we said a bunch of things, but we think it's going to... Yeah, it was the answer. The thing I did, I think I just erased, actually. And the arguments we were making, they're giving us the answer. How are you going to do this? What do you want to say about it? Well, I'll tell you what. This negative I rho, it's made easy enough for us. Just leave it. My erasers have kind of reached the limit here, but let's see what we can do, guys. We're not going to give up on this. We can do it. The negative I rho over pi, and let's talk. I mean, let's talk a bit. You know that's not going to change at all. It's a constant. If it's a constant, leave it alone. Plug in L and see what you can say. I mean, there's so many ways we can kind of argue with it. If you've got it like this, and I might go just against my notes a little bit here, not much. As we have all this, we know we have all this. What is a negative 1? What is a negative 1 times a negative I rho over pi? A negative 1 times a negative I rho over pi is a positive I rho over pi. So, tell you what, let me get rid of that negative. Negative times negative is positive. Maybe this makes things a little easier to look at. And again, these erasers become more of a joke the more I use them. So, all right, let's argue it like that. Why not? Do we have to? No. You can leave it alone, and you're going to get it right. If you're consistent with the mathematics, this is not going to be an issue, guys. We're not going to make an issue out of it. Let's talk. Try to abbreviate as much as I can here, I guess. This is... There's a whole lot can be said here, I guess. Let's see. Is there more I can say? Yeah, what the heck. There's a whole bunch more I can say. The L over the quantity B minus A, that's also a constant. You might as well just bring it out. I rho L so I'll tell you what. I'm going to make this I rho L over correct. See those subtractions and find out what it is. Stuff should be, let's do let's evaluate. X equals L. Put an L right here. X equals capital L. Put a capital L right here. A capital L right here. Capital L and capital L. Capital L on top, capital L on the bottom. They cancel. You got B minus A plus A, which is B. Which is B. Let's see here. So we got B to the negative 1. Yeah, that's B to the negative 1. Let's just cut to the chase. That's 1 over B. Put a 0 in here. 0 times this is 0. You got an A. That's a to the negative 1. That's 1 over a. Yeah, that's it. You're about done. We have right. Okay. Let's just keep going. This is 1 over b. This is 1 over a. I'll tell you what I'm going to do. What do you say I multiply top and bottom by a? It's 1 over b. If it's 1 over b, what do you say you multiply top and bottom by a? If it's 1 over a, what do you say you multiply top and bottom by b? So what we end up getting is I rho L over pi b minus a right. So we got this. This right here is a minus b over ab. True. Right. A minus b, it's like 10 minus 3. Or, I'll tell you what, this is a minus b, it's like 3 minus 10 is negative 7. And this is like 10 minus 3, which is positive 7. Negative 7 divided by positive 7 is negative 1. A minus b is opposite in sign, but exact same size in terms of magnitude as b minus a. A minus b and b minus a are the same magnitude, but opposite in sign. They cancel, but there's a negative 1. They differ in sign. If this is a positive number, this is a negative number of equal magnitude. If this is a negative number, this is a positive number of equal magnitude. When they cancel, you get negative 1. When you do that, you guys, you look at some of the notes on that, how they're saying, and like it kind of goes back to what I was saying earlier regarding magnitude, how you can sort of ignore a negative sign. You can't really do that, but you got to kind of know for bookkeeping, there's a lot that can be said. So let's kind of finish the argument on this whole thing. What you're talking about is V or delta V, V being equal to delta V in this case, the change in potential. It is going to come out, as we said, these are going to cancel. B minus A goes into A minus B negative 1 times, guaranteed. So what you end up getting is, you just get I rho capital L times negative 1 over pi AB. Right. I rho L times negative 1 over pi AB. I rho L times negative 1, or negative I rho L, or negative Li rho. Doesn't really matter, guys. I'm trying to stay consistent with my notes. Li rho over pi AB. True. What does that mean? That means the magnitude of delta V is a positive Li rho over pi AB. That's it. Yeah, that's true. We're talking about, like I said, the way we're doing here, at the end of the day, guys, magnitude's going to win the day. I mean, let's know what we're doing here. You're saying there's a negative sign here? Yeah, okay. The big thing is there's a potential difference. Depending on what direction we're going and all this other stuff, but in terms of magnitude, we are there. In terms of magnitude, we got this thing under control. We're getting this in terms of the magnitude. Absolutely. Absolutely. Okay, great. So what? Well, if you remember what I said last time, there's a bit of a, let's see what we can say here. We're coming back to Ohm's law. What's going on here? Well, V equals IR. R equals V over I. Yeah, I guess if there's a lot of voltage and not much current, big divided by tiny is huge resistance. If there's a lot of voltage, and a small amount of current, great amount of voltage to actually try to facilitate a current flow, but there's not a lot of current flow. Huge divided by small is a big answer. Yeah, there must be a lot of resistance. If you put forth a lot of voltage and you don't get a lot of current, makes sense to me. If you have a small voltage, but you still get a lot of current, what's tiny divided by huge? Really tiny. Yeah, it must be a small resistance for something like that to happen. Well, let's use that then. V, or delta V at least, right? Magnitude of delta V is Li rho over pi AB. Li rho over, forgive me, Li rho over pi AB, then over I. I'm sorry, forgive me here, guys. Let me try to get a little more based on what I said here. Let me try to put the R right here, and then go V over I, and then let's run it from there. Li rho over pi AB, that's the voltage, you got it, divided by that's it. That's all it is. The rest is the formality. That's it. The I and the I cancel. The I and the I, they cancel. Kind of interesting. If A and B are big numbers, if A, this is a lot going on here. This is actually the area of an ellipse, and I talk about that elsewhere in quite a bit of detail. That's fine. The A and the B are present in the problem. The A and the B are present in the problem. If A is big and B is big, that's indicative of big areas. Didn't we say that big areas tend to offer less resistance? So something associated with big areas, big down here, big divided into something tends to give you a small resistance. Pretty important. If L is long, if capital L is long, the longer something is, the more tendency it has to resist. Wait a minute, we said that earlier when we were talking about didn't we say that? Yeah, we sure did. If that looks a lot like this, yeah, there's a row essentially on top. Yeah, the fact that it's in the middle means it's on top. It's in the numerator, certainly not the denominator. Row right here means row in the numerator. Row on top. There's an L. Yeah, really? Well, here's a row, here's an L. Great. This is indicative, if you allow me to say, kind of, sort of area. If A is a big radius, then the small circle associated with the small radius A is actually a big circle. It's just not as big as this circle. I'm just saying, if the small circle if the small circle in this problem, if the smallest circle in this problem has a really big radius, if the smallest circle in this problem has a really big radius, then it has a really big area. It's still potentially much smaller than the very large circle, but if that has a very big radius, that's also a very big area. All the cross-sectional areas are between small area and big area. But I already told you, if A is big, it's still a big area, even for the small one. And if B is big, it's still a big area for the big one. That means everybody in between, bigger than this, but smaller than this, are big areas. Didn't we say over here, you guys, that the resistance is directly proportional to the resistivity times the ratio of capital L over A? You know, you can write it. I mean, I'm not going to be petty about it, guys, but let me put a row right there. Let me put the L right here. And that pi AB, on average, in terms of the mathematics, it behaves, and I've said this before, the resistance present behaves as though you had a cylinder, not a cone, a cylinder composed of, you had an elliptical cylinder that had a constant cross-sectional area equal to pi AB. If you had a cylinder that was elliptical in area, and that's B, and that's A, and that's B, and that's A, that area is pi AB. That area is pi AB. And if you run at a distance L, and it's the same material with the same resistivity rho, the resistance going across this distance is exactly the same as the resistance taking place there. And I've discussed that elsewhere. That's pretty fascinating stuff, you guys. I mean, it comes out, and again, the symbolism is really the non-numeric symbolism wins the day. Because if we understand this with the non-numeric symbolism, then with the actual numeric answers that we're striving to get them is quite easy. We understand the non-numeric symbolism. Okay, so, and I wrote it essentially the same way in my notes. This, I think, is a stronger statement when we're doing something like this, you guys. And there it is at the end of it. Okay? If you plug in the actual, you know, for whatever's going to go on here, so let's see. Plug in all the appropriate values, and we're given the answer key in the Halliday and Resnick book is giving us this. I think I might have worked this out as well. Sometimes I just take their word on it because I didn't have a lot of time to run through some of this stuff. They're typically pretty strong. Nobody's going to, you know, they're not going to be perfect in their evaluations of it. We're all going to make mistakes sometimes, but I think this is right. I think I confirmed this as well. If not, I just went straight from what they have. I always try to look at what they're doing regarding a numeric answer. And here is the numeric answer, ladies and gentlemen. (9.81 times 10 to the fifth). 9.81 times 10 to the fifth ohms. That's a resistor that is really resisting a lot. You got to remember what were the radii? Yeah, the radii weren't like 2.3 meters or something like that. I think the radii that they were talking about, if we're careful about it, right. The radii under consideration are 2 millimeters and 2.3 millimeters. A is 2 millimeters, B is 2.3 millimeters. That's tiny. Well, of course, then we say the area being very small, resistance is inversely related to the cross-sectional area and or aggregate cross-sectional areas that are under consideration. What sort of kind of like weighted average is taking place here in a sense. I went into this in other detail, in another discussion. It's the same basic arguments. You can look at that in that video as well that pertains to a similar problem from this. That was in the Katz book that I'd actually done that. I'd looked at it in the Katz book. Okay. Nothing incredibly profound. We just sit down and look at the mathematics. It's relatively basic mathematics, but fascinating nonetheless. It's a lot of fun. Just a lot of fun to look at it. And look at it, guys. We're talking about A was a radius of 2 millimeters. 2 millimeters? A was a radius of 2 millimeters. B was a radius of 2.3 millimeters. Well, that tiny? Wow, it's inversely related. Resistance is inversely related to the area. That's a tiny area. Pi r squared, when you're talking about millimeters, 2 millimeters or so, it's a very small answer. So you're going to get big resistance. Okay, that's looking good, guys. That's what I wanted to talk about. Thank you for your time. Take care.